This is the first part of the lecture and in-course introduction for radioactive materials handling course, RPT 233. As you can see, it is the intro as well as a review. And this review is going to cover some things that really you should have already become proficient at using, although you may have had a semester or two possibly where you've not used them. And so we want to review some things. And then the equilibrium. Some of you have had the specific instruction regarding that in one of your previous classes. Some of you may not have. And because of that, we want to make sure that we address this, because you need these tools. You need a refreshment. You need a clearer, crisper understanding of some of these topics, but also this equilibrium because of the nature of radioactivity. As you'll see, there's actually a mechanism by which we may make errors, and we want to understand what's going on there. Prior to getting started, I do want to just make sure that you've got the right course material as well as the syllabus. And the syllabus addendum that would be located on your Blackboard shell. I need to make sure that you also have the proper reference material and textbooks. Of course, the nuclides, charged nuclides that you've used throughout the course, we'll still be using that, and without a doubt we'll still be using Radiation Protection Technology by Daniel Guldick as our main textbook. Also, there will be another one that's provided, or that is required. It's over in the bookstore. And that is Radioactive Waste Management, 2nd edition by Sailing and Fenneman. We'll draw on this time to time, not extensively. We don't follow it chapter by chapter, but you do need to have one in order to be able to complete the course. So I recommend that you get one from the bookstore for that purpose. Now, as always in all of our courses, we will go through and pick up the learning outcomes at the beginning, and as we go through the instruction, this is where you need to be measuring. This is where you need to be looking. This is what you need to know. And so with that, you can see the two here, and really that is the bulk of the instruction. Only 2 learning outcomes of a lot of material. We're going to look at complex decay schemes such as natural decay schemes. There are 3 major ones that we look at. We'll also take a look at some reactor-produced decay chains, isotopes that are produced as part of the fissioning process, or even possibly as part of the activation process that occurs within an operating power facility, as well as within accelerators and research laboratories. And then finally, the equilibrium aspect of this. Equilibrium isotopes, you'll see we have secular, transient, or no equilibrium that may exist depending on the characteristics of the different isotopes. So we'll be talking about that as one of our learning outcomes. And then additionally, you'll see that we will be going back to the charged nuclides, where we'll be able to trace the decay of a radionuclide and all the way down to the stable end product. As we go through it, you'll see we'll start with the introduction, look at some identified basics that we want to make sure that you're up to speed on, and then we'll hit the equilibrium. As always, questions are encouraged. If you're doing this online, you have availability of chat, as well as some other tools available on the Blackboard. And always you have email. So questions are encouraged. As far as the introduction, so far in your educational process, we've talked about radioactive material, and really from the definition standpoint of very basically what it is and how it does what it does and why it does what it does. But it's been in a general term as far as how do we classify it, how do we handle it, what do we need to do as far as precautions for packaging, transportation, things of that nature. In this course, we're going to take a brief refresher on the fundamentals, but we're also going to get into some very specific items regarding regulations, control, use, movement, storage, rad waste, transportation of radioactive material, and then as a closeout, we're going to talk about decontamination. Some might say, well, why is that in the course having to do with radioactive material handling? Well, decontamination is removing radioactive material from places where you don't want it to be. And the result is you generate radioactive material. So we need to talk about that and understand the basics involved in how it is fit into the entire radioactive material handling processes. Here are some basic terms. Again, we've talked about this over the course of your time in the radiation protection technology. But nuclear stability is a basic one. And that really goes to identifying or defining radioactive material. What makes something radioactive? It's nuclear stability, or actually lack of nuclear stability, that causes it to be radioactive. And it really does boil down to a balance of forces. And that balance occurs within the nucleus of an atom. It's a balance of gravitational forces, of electrostatic forces, of nuclear forces, things that hold the atom together, the forces that are involved there. Now, as far as those three gravitational forces, relatively small, we do not consider it on the level at which we approach this, but we do consider the electrostatic force, which is very significant. And when we're talking about electrostatic forces, it's helpful to remember that has to do with the attractive and repulsive forces between charged particles or charged items. And of course, opposites attract, likes repel. That is the electrostatic force acting. And an example from a nuclear or an atomic level would be the protons. Protons within a nucleus, they both have positive charge on it, and so you would expect them to repulse. They would push away. But for some reason they don't. For some reason within the nucleus of an atom, these protons are able to reside adjacent to each other regardless of that electrostatic force that's trying to push them apart. And that brings us up to the next force, and that is the nuclear force. Nuclear force, as you can see, is independent of charge. It's equal between neutrons, it's equal between protons, and it's equal between neutron and proton. It has a very short range as opposed to the electrostatic range, which has a fairly hefty range. Electrostatic force has a fairly hefty range. The nuclear force is very close in. It's very strong, but not out beyond a certain point. In fact, beyond a certain point, the electrostatic forces do take over as the stronger force. Now, it must be understood that since that electrostatic force range is so much larger than the nuclear, in order for an isotope to be stable, there must be more and more neutrons in comparison to protons. And that takes us to looking at the number of neutrons and protons in a ratio, understanding of a ratio. Now, we'll get to it here in a second, but as we take a look at the neutron-proton ratio for existing isotopes, we'll find that that does indeed determine the stability of the isotope. And for an atom, for a specific isotope to be stable, that means that the forces, the nuclear and the electrostatic forces, are balanced. They're canceling each other out. When they become unbalanced, then we can say that the atom is no longer stable, and if an atom is unstable, then it's radioactive. That defines a radioactive atom, one that is unstable. And it can be unstable for a variety of reasons, but basically it involves the imbalance that exists between the forces that are going to holding that atom together. Up to a Z, which remember, Z is number of protons, determines the element. Up to a Z of about 20, the ratio of neutron to protons runs to 1 to 1. The 1 to 1, 1 proton to 1 neutron. Now above a Z of 20, we'll see that the ratio of neutrons to the number of protons must increase to maintain stability. In other words, when I start getting more than 20 component parts, or protons within a nucleus, then the repulsive force, or the nuclear force starts getting outside of that range to where it can hold everything together. And so, in other words, to maintain stability, I've got to put more neutrons in there to separate those protons so that that electrostatic force is no longer able to repel. Increasing the distance between the two like charges diminishes the effect of that electrostatic force. So we need more neutrons, which means the ratio goes up as we get above 20. Now, as you can see, Z equal about 83, which is bismuth, the element bismuth. The ratio starts to exceed 1 to 5. And it's that 1 proton to 5 neutrons. Above bismuth 209, there are no stable isotopes on the chart of the nuclides. In fact, at bismuth 209, I believe the ratio is like 1 to 2.2 or something like that. It's quite skewed. And so now we've reached a point where really nothing's going to hold that together. It's going to be unstable, anything above the bismuth 209. And it will undergo some type of radioactive decay. Looking at a chart of the nuclides, you can see that, and this is a plot of all elements, all isotopes, and the horizontal axis is the axis showing us the number of neutrons, which is the A minus the Z number. The number of protons is represented by the vertical axis, and as we plot along, you can see that if we go to the 20, which you can see there, the 20 neutrons as compared to 20 protons, ratio of 1 to 1, you'll find that intersect a black square. The black square on this chart of the nuclide represents those atoms that are stable. And running up between the charts greater than 20, we start seeing that the number of black squares actually get higher and higher and higher, such that you wind up with a curved chart of the nuclides. And if we were to plot the 1 to 1 with a dashed line, we'd see it's right there. And so the stability, line of stability, actually comes in below that 1 to 1 ratio, which means we have more and more neutrons per proton. That ratio gets bigger and bigger and bigger. Now that ratio is actually 1.5 to 1. Isotopes to note, the line of stability on our illustration here with the black boxes as they go through are actually anything above that line of stability is radioactive, and it would tend to decay through beta emission. So it would move down and to the right, beta minus emission. Anything below that would tend to decay and move up to the left in an upward direction. The isotopes that are in the far right-hand side of this tend to decay by alpha emission. These are the heavier isotopes, very unstable. Must get rid of a lot of mass out of the nucleus in a short period of time to attempt to reach that stable state that is no longer radioactive. And you can see there's a gap there. But they would decay, they'd lose 2 neutrons, and they would lose 2 protons, so they'd go down 2 and to the left 2, to the daughter product. And we'll get to that, more about that here in a second. Although it is important to determine stability, the ratio is not critical. An element may have several isotopes that are stable, sometimes as many as 10. So you can see that the ratio can vary quite a bit within a specific element. And also for a given atomic mass, there can be several isomers that exist. And that is the ones with the same mass number but different number of protons, different Z number. Now, as we've already alluded to, that's nuclear stability. And in order to remove itself from being unstable and reach stability, those that are unstable take on this thought of being radioactive. And it is a characteristic by which an atom with excess energy is in the process of trying to reach that stable environment. This involves some change or transmutation of the atom's nuclear configuration. And it is referred to as radioactive decay. That transmutation or that radioactive decay can really be seen as a disintegration. It's a breaking down of, it's an attempt to reach that stable state. And as such, we can say measurement of radioactivity is the number of disintegrations that are occurring. Anything that is unstable, an isotope that has that lack of stability and is undergoing decay, oftentimes can be referred to as a radioisotope. It's a radioactive isotope, combination of two words. Moving on, after the change, that transmutation that occurred, it may be stable, it may have reached that stable state, it may not be. And so, if it's unstable, it'll continue to attempt to reach stability by the emission of some other either radioactive particles or energy, which we call pure energy, which we would call photon emission. The amount given off is dependent upon the configuration just prior to that emission. The atom that is radioactive to begin with and starts this whole process is considered the parent. The isotope that remains after the emission, after the decay, is referred to as the daughter. If the daughter is radioactive, then it becomes the parent and decays to the subsequent daughter, and so on. When we're looking at radioactive activity, we can split it down into a couple of basic categories. First of which would be I'm sorry, let me back up here a second, I skipped the page. But as we trace these steps, these transmutations, these attempts at reaching stability, we then have this thing we can refer to as a decay chain. It's the process by which the isotopes reach stability and the transmutations that occur along the way, as well as the energy or the particles that are emitted in that ability or that desire to reach stability. Now, back to the categories. Our first category of radioactive material, or radioactivity, would be a naturally occurring radioactivity. It's just what it says, naturally occurring. There are 42 naturally occurring radioisotopes, and they, in essence, come from 3 decay chains. You can see them listed: the thorium-232, the uranium-238 series, and then the actinium series, which is uranium-235. Every single one of these decays, going down to stability, end up in some stable isotope of lead. Go figure. Now, while we have these 3 natural ones that are shown here, when I said there are three chains, there's more than 3 chains, but these are the naturally occurring ones that are most common. And it would appear by looking at these that they're all heavy isotopes. Well, that's not the case at all. There are some lighter elements that are involved, and this is a depiction of some of those, of the prominent ones, potassium-40 being probably the most familiar one. That's the one that we have within our bodies. That's the one that's found in bananas. That's the one that can be found in water softener. And then on down, you can see rubidium, samarium, and Lu and Re. I forget what the elements names are there. You can look those up. But they are all naturally occurring. And you can see the half-lives are all in the order of many, many years, buku years. It's interesting to note that only one of them is an alpha emitter. As I pointed out earlier, most of the alpha emission occurs high in the heavier elements. And so we have one here that is an alpha emitter, and then the remaining ones are beta and gamma, and possibly sometimes both beta and gamma. So that's naturally occurring. If it's not naturally occurring, then we'd say that it's artificially produced. It should be fairly obvious that artificial radioactivity has not been around forever. It had to start somewhere, and basically it started with the work of Curie and Joliot in '34, where they took an aluminum atom and they bombarded it with an alpha. And they made a radioactive isotope of phosphorus. Interesting. Now this is all part of the research work that they were doing using radium. Radium is an alpha emitter, so it would make sense that the experimentation that they would have would come from the use of radium, but the production of a measurable radioactive isotope by man started the era of artificial radioactivity. Now, today, that's done in a variety of different ways for a variety of different purposes. Obviously, as you can see, operating a nuclear power plant does create radioisotopes, or produces them. It's produced through activation process of crud. You've studied crud, you understand about that. But it also is the production of fission products, a byproduct of the fissioning reaction which we use to make electricity. Accelerators also are a source. They bombard stable atoms with charged particles, activating them, they become radioactive. Some of this is done for medical research, some of it's therapeutic, diagnostic possibly. But in general, what we can say is that all of the artificially produced radioactive isotopes will move somewhere towards stability. They'll undergo radioactive decay and the emission of particles or energy and attempt and to ultimately reach stability. In general, what we can say is that heavy radionuclides, both natural and artificial, decay by a long line of alpha and beta emissions. The lighter ones, they will decay mainly by beta negative and beta positive, as well as gamma. Usually beta decay will be accompanied by gamma, something that you should know. And there will be fewer steps involved. It won't take as long for them to get down to stability, or at least as many steps to get there. With each transmutation, an emission from the nucleus occurs. When it's reaching that stability, as we've said, some particle or energy will be emitted. And that is referred to as radiation. Roughly defined is the particles or energy that are emitted from the atom in the process of undergoing transformation involved with reaching stability. Now what we're going to do now is we're going to go through and take a look at some of the decays, some of the types of radiation. I'm not going to spend a whole lot of time on these because these should be second nature to you. We just want to refresh you in them. And then that'll be followed by a quick review of the chart of the nuclide and how to trace radioactivity on the chart. And with that, we're going to take a short break, and we'll return in just one moment. Well, welcome back. And before we go into the types of radiation, I do want to correct a little bit of a misstatement I made there earlier regarding neutron-proton ratios. The neutron-proton ratios, it is neutron to proton. Starts out the 1 to 1. Above 20, we're looking at 1.5 to 1. That's neutrons to protons. As we start getting into the heavier elements, above and at bismuth-209, you're at about a 2.2, 2.3 number of neutrons to each proton. I had misstated that earlier, and I want to make sure we correct that. So let's take a look at the types of radiations that are involved. They do dictate, the radiation that's emitted dictates how we refer to the decay. So an alpha emission is an alpha decay. A beta minus emission is a beta decay, gamma decay, positron, as well as a neutron. Those are both radiations that are emitted and the type of decay. As we move through these, as I said relatively quickly, the characteristics associated with an alpha decay, of course, an alpha is a particle, is a charged particle, as you can see on the illustration on your screen. In essence, what it is a helium atom without the electrons, which means it's the nucleus of a helium atom. It has 2 protons, 2 neutrons. Without the electrons, it has a net positive charge of 2, which is a highly charged particle that has a really good mass on an atomic level, because you've got 4 AMU. And so we have this charged particle, big charged particle with a big charge. That tells us that it's going to be very reactive, it's going to interact readily, and because of that, it means that it can be easily shielded. We see the alpha decay mostly in the heavier elements. As noted earlier, the easy shielding can be really a simple matter of placing a piece of paper over the source, and you can shield it away. The layer of dead skin is a good shield for alpha. It is primarily an internal hazard because of that. And the reason is, inside of us, we have live tissue. We don't have dead skin, we have live tissue. And it will interact, and as we said, it'll interact a whole lot because of the charge and because of the mass. As far as illustrating it, the alpha decay equation is illustrated here. Let me point out that the arrow there, you can look at it as an equal sign. And as equal, we must maintain a balance between mass and energy between the 2 sides of that equation. On this example, we start out with plutonium-239. It undergoes decay to an alpha decay, which is indicated by the 2-alpha-4, plus the resulting isotope, uranium-235. Now, I will add that this alpha particle and possibly the daughter product that's shown here will both possess some level of kinetic energy, whatever is needed to balance the equation. And that really starts with what is the overall energy state of the parent, plutonium-239. As far as steps on any of these, the basic steps that are involved, if, for example, we're going to plot the decay equation for alpha decay of radon-222, we would first set up our equation. We've got the parent, which is radon-222. It's going to alpha decay to a daughter, and the daughter we don't know. We're going to find. The mass number is going to go down by 4, so the A is going to be reduced by 4, the new A number being 218, and then the atomic number will go down by 2, maintaining mass balance. It goes down by 2, which gives us a new Z number, atomic number of 84, changing the element that's involved. I go and find out what the element 84 is, and that's polonium. And so to complete my equation, I would add that, and this would indicate the alpha decay of radon-222. Now the beta minus decay occurs when we have a situation where we have a neutron within the nucleus undergoes transmutation into a proton. The mass of a neutron is a little bit more than the mass of a proton, and so that difference in mass, that excess mass after that transmutation, results in the formation and the ejection of a small particle from the nucleus, and that is the beta minus particle. You see the annotation there using the standard XAZ notation. It has the same mass as an electron, 0.00055 AMU. It has a little bit different, smaller energy adjustment than an alpha. You may note on that previous slide that with the alpha explained that it's the most energetic. We also can say, remembering that it is a conversion of a neutron to a proton, and interestingly enough, the energy of that beta will not be monoenergetic. In alpha decay, the energy of that alpha is monoenergetic for a specific isotope. That plutonium that decays, the alpha coming off that, I can say definitively, time after time, it is a monoenergetic. It has a specific MeV energy that it carries away from that reaction. Not the case on beta. It's a spectrum, all the way from down here next to 0 up to some maximum, which is called Emax. Typically what we do is we assume that the average energy, if you will, is 1/3 Emax. 1/3 Emax. Now as I write this out into an equation, I can see again I'm still balancing the sides, and I've started out with, say, for example, a tritium atom here that you see. It undergoes beta minus decay. It gives me that beta minus particle. Now I've got to keep the same balance, right? And so the resulting daughter product is going to have a Z of 2. Balance those two numbers, the two Z's on this, balance that back out to 1. And that's what I've got to maintain. Well, that's helium. And the isotope of helium you can see that it represents is the helium-3 atom isotope. And then this little V with a bar above it. This is the antineutrino. Now, it plays a couple of roles in our beta minus decay. Remember I said that the total energy emitted is a spectrum. And typically we say that the energy being emitted by that beta particle coming off of a beta emission is going to be 1/3 of Emax. Well, what about the remaining 2/3? The remaining 2/3 must be accommodated. It must be accounted for. And this is what the neutrino, it is a particle, and it carries away the remaining, the balance of the energy. And so if, for example, my beta emitted is actually 2/3 of Emax, then that antineutrino is going to carry away the remaining 1/3. That is the balance that must be maintained between mass and energy between the left side parent and the right side daughter. That is Emax, antineutrino. Other things to observe there, as we've just said, it is always accompanied by an antineutrino. Another thing to say about an antineutrino is that because we are dealing with something that that has mass, has energy, but interestingly enough, until 1950s, it had never been detected. It was all theoretical. But in 1954, I believe it was, at Savannah River Station, in conclusion to some experimentation that had been being conducted trying to prove the existence of neutrino, they actually were able to detect one, an antineutrino. And so now theory moved into fact. It's very difficult to detect it because it does not interact readily. It goes on and on and on and on and on and on, and eventually someday, I guess, it does deposit or shed the kinetic energy that it has, but it's very difficult to detect, and because of that, it's really of not any measurable consequence to radiation protection, because we really, are concerned with things that cause biological damage, and to our knowledge, antineutrinos and neutrinos do not do that. The thing to know also is that a beta minus is shielded by low Z material. A higher Z material is not desirable because of an effect that is called bremsstrahlung. And describing bremsstrahlung, what we need to understand is this, that it only will exist. Let me get my other camera up here. It will exist where we have a large nucleus and because of the size of this nucleus we can say that it has a rather large electrostatic force that's associated with it. And of course we have the orbital electrons that go around that are associated with this nucleus, but they are in their orbit. And what happens is that with this large nucleus we have a high energy beta minus particle. And as it passes near that nucleus, it will come under the influence of the electrostatic forces from that nucleus, from the protons. Not enough, and it's not close enough to actually be pulled into the nucleus, but it is close enough to be affected by it, and as it is affected by it, it changes direction. It changes its direct trajectory. And in changing that trajectory, it will actually, overall, it will actually slow down. The energy of motion is reduced. Now, we must maintain, again, the balance of energy, and the way that that is accomplished is at the point after it starts braking, slowing down, it will emit a low energy X-ray. That low energy X-ray is referred to as bremsstrahlung. And as you might surmise, that is German. And what it does, what it stands for is braking radiation, or slowing down. It's energy radiation that's emitted as a result of that high energy beta particle coming in close proximity to a large nucleus and coming under the influence of that electrostatic forces of that nucleus. Now, as we continue to look at the beta minus, again, it's just an illustration of how we go about resolving a beta minus decay equation. Again, keep in mind balancing left and right side, mass and energy. We're going to have a potassium 42 undergoes a beta minus emission. Beta minus, you'll see it illustrated here with the E as an electron. It's because it's for all intents and purposes, it is a free electron. It's the same size, same mass, and the same charge. And so we just use that nomenclature. But you can also see it with the beta, the Greek alphabet beta as well. Either way is accepted. Our mass number stays the same. My atomic number's got to go up one to maintain mass balance on either side, which means my resulting Z for the daughter is going to be 20. And if I look up 20, that's calcium. Balancing my equation, I wind up with this. And do not forget the anti-neutrino, because it must be there to carry off and account for the energy that's not taken up by the beta minus. Beta plus is very similar. With this reaction, though, we have a proton that is transmutating into a neutron. And in that transmutation, a beta plus is emitted. Some texts, including Goldnick, refer to that beta plus as a positron. Now, that's really not accurate. And the reason it's not is because if I had an electron and a positron come together, and I'm just thinking of it in terms of the electrical charge, what would happen is that the electrical charges would cancel each other, and we would wind up with a neutral charged particle that was twice the size of what it began. Well, that's not what happens. It actually, if a negative beta minus comes together and a beta plus comes together and they meet, they will actually annihilate each other. So in truth, it is an anti-electron. But we'll call it a beta plus and a beta minus, and you'll also see it referred to as positron. And so it's an anti-electron. very similar again to a beta minus decay, small energy, conversion of proton to a neutron in this case. And again, energy is emitted over a spectrum. Now, as you can see in our example down at the bottom with sodium-22 decaying to neon, the little particle that completes the equation here, instead of an antineutrino, we have a neutrino. And a neutrino serves the same function in a beta plus that the antineutrino serve in the beta minus. Same shielding characteristics, low Z material, and high Z material again would also cause, except in this case it would push it away, causing it to again slow down and cause the brimstone. The equation, just to make sure we get that in there, same process is followed. And do not forget the neutrino for the beta plus. The next one we want to talk about is the gamma emission. The gamma emission occurs when a nucleus has an excessive amount of energy. For whatever reason, its energy state is elevated, and it attempts to reach stability. It attempts to reach stability by the emission of that energy. Boom, a pure packet of energy is emitted from the nucleus. No mass, no charge. That is referred to as a gamma. No mass, no charge, pure energy. It originates in the nucleus, and as you can see, the Z and the A do not change. It will often accompany a beta or an alpha emission, and is usually, when one does occur, it balances that energy balance need. It satisfies that energy balance need. It must occur. Now, I do want to point out that as far as its physical characteristics, a gamma and an X-ray are really the same. They're both no mass, both pure energy. The only difference is that X-rays tend to be a little bit less energetic, not as high of an energy level. But the biggest difference is, where are they born from? As gamma, you can see, is born from within the nucleus. And X-ray, as illustrated in the Brimstone illustration, is born external to the nucleus, somewhere out in the orbital electron area. And so that's the biggest difference, and that's the distinguishing difference between X-ray and gamma. As far as writing up an equation, what I want to illustrate here, and as you see the asterisk that's there on the slide, let me also point out that that can also be replaced by a small m. A small m represents a metastable state. Let's talk about that just very briefly. A metastable state, such as the case here, as I said, it could be illustrated there. In the chart of the nuclides, if we were to look at xenon, we would see xenon 131 for this isotope, and the bottom part would be listed or split in half. It would be split in half. On this side, we likely are to see this isomeric transition. On this side, I'd have to look it up, and I do not have that immediately available. Let me take a quick look of the xenon. Let's see if I can get it on here, and it'll be a little easier to see maybe. The Z is 54, and so I'll find that on my chart of nuclides, find the isotope 131, and as it turns out, the isotope for xenon on the right-hand side is stable. Let's see if I can zoom in on this thing. There we go. The xenon 131 isotope is shown here As I said, this side is split. It has an IT 163.9. And what that tells me, the 11.9 is my half-life for this side. And these always decay from left to right. And so this xenon 134 metastable will decay to the xenon 131, which is a stable isotope. The 21.22 or 2324 is percent abundance of that isotope. But the gray color there indicates that that is a stable isotope. The rest of these colors you can look up and see what they are. This is the isotopic mass for xenon 131. But what I also want to point out is the nomenclature that's used. The xenon 131M metastable represents this side. If I just have the ZE131 without the small m, that represents this side of the box. Now you'll also find some that are radioactive on the other side, and you can just look down the chart here, just a couple of blocks and you find one. Xenon 133 exists in two states. The metastable state, which is on the left side, has a half-life of 2.19 days, isomeric transition 233.2. That's the energy level of the gamma. It decays from the left side to the right side to xenon 133, which is a radioactive isotope. It has a 5.43 day half-life. It undergoes beta minus decay. And you can see that the value of the energy 0.346, that is the E max. That is the E max. So with that explanation, we'll move on. But I did want to make that distinction because that is a point of confusion sometimes for students. Let me zoom back out. Oops. Yeah, wasn't that exciting? So, that's my gamma emission. We will move on from here into the next type, and that is electron capture. Electron capture is a condition where you have an orbital electron that is actually sucked in to the nucleus. Is captured by the nucleus. It disappears, and it goes and basically combines with a proton to form a neutron. So the proton number goes down, the Z number goes down by one. New element. So it's a electron capture. In that respect, the proton to neutron conversion is very much like a beta minus, beta plus, but no beta particle is emitted. You wind up with a K-shell electron, typically is what it is, the inner shell electron, that must be filled, and it's usually filled from the outer orbits, and as they fill from higher energy levels, they have excess energy, too much energy for that orbit, so they emit an X-ray. An X-ray. Mass and energy must be balanced. So let's take a look at beryllium 7. It undergoes electron capture. Here's how we annotate that. The resulting daughter product would be Z number of 3, which is lithium, and our balanced equation would show this. Now, in this particular case, you see the lithium with the asterisk. That is an indication that that is a metastable state. And if we were to look up the lithium, 3-lithium-7 on our chart of nuclides, we'll see that indeed that is that's not what we would expect based on our previous discussion. Let me see if I can get that in our... Oh, the wrong way, sorry. Look. What we can say about lithium-7 there is that it's a stable product. In our illustration, in our decay equation, we show an interim step there. And this is an interim step that really is shown just simply because we've got to show that somehow that energy must be resolved. And so we show an interim step, and in that transition or change from that interim step to the stable step, an X-ray is indeed emitted. And that takes care of the excess energy that was shown. And the final type of radiation we're going to cover here is the neutron. Now, a neutron, as it's contained within a nucleus, is not considered to be a form of radiation. It's part of the nucleus. But when that neutron is free from the nucleus, and it is a free neutron, then it's radiation. It is a particle with mass moving with kinetic energy and interacting with material and matter. In particular, we're interested in the interaction that it has with the biological system, us. And as you'll see, that is our major concern with neutron as far as our radiation. It starts out, of course, as a major component within the nucleus, but when they do become free, they become forms of radiation and particles that can cause other reactions, such as fission, and that's what's illustrated here. As the slow neutron comes into a fissionable material like U-235, it will cause U-236, which is unstable. It will undergo ultimately a fission reaction, which in this case will result in the formation of fission fragments, shown here barium and krypton. The flash that you see there represents the energy that's released, thermal energy that's released, as well as 3 fast neutrons. These are neutrons with an excessive amount of kinetic energy. This is the byproducts of, these are the byproducts of fission. Now they will go on, the fast neutrons will go on, and they will interact with matter as they transfer their kinetic energy, and it's that interaction that we're concerned with, that we need to be concerned with as far as it being a form of radiation. There are no electrical charges associated with it, so that tells us that pretty much transfer of energy is going to have to be by collision, direct contact. It can be released spontaneously, which is rare, although there have been known to be some natural isotopes that do emit neutron radiation. But by and large, it's generated either through isotope production or power reaction, such as fission reaction causing these fast neutrons. And as I've said, because they have no charge, they pretty much have to interact by direct contact. The interaction that they have will either be elastic or inelastic, or it may even involve an activation process. Typically within the human body, it's the elastic and inelastic scattering that occurs. In a power plant, activation is really the major concern, because what it does is it takes an otherwise stable isotope, creates or causes it to become radioactive, which then we must deal with because of the radioactive decay that follows. Now, as far as the chart of the nuclide, and we'll go back to this, we want to talk about how to use the chart a little bit. Let me, I'll click through the slides, but also want to show you in the handbook, or in the chart of the nuclides, some of the decay that occurs and how to trace it on here. And this really should be, again, be a review for you because we've done this all before. Let's start with switching this over. We'll start with zoom back out. We'll get there in a minute. In the example that I want to use, let's see if we can. Here, let's use thorium-228 as our example. You can see there's a lot of information on this chart. The thorium-228 is radioactive. It has a half-life of 1.912 years. That's what the A stands for. The main mode of decay is alpha emission, and you can see there's more than one alpha. There will be, and these are the energy levels of those alphas. Now, when you're tracking an alpha decay on the chart, of course, we're going to be losing 2 protons and 2 neutrons. I'll tell you what, let me move up to uranium-232 so I can do everything here on the same page. Here. Uranium-232, 69.8 year half-life, undergoes alpha emission. Again, there's 2 energies listed here for the alpha. But when we're talking about alpha decay on the chart and tracking it to the daughter that would result, the alpha that would result, all we have to do is keep in mind what's happening in that transmutation. What's happening in this transmutation is I'm losing 2 protons because the alpha takes two protons away, so I go down 2, 1, 2. I'm also losing 2 neutrons. And so it goes down 2. Remember, the horizontal axis is the number of neutrons. So it goes down 1, 2. The daughter resulting from that decay is going to be where we started at, thallium-228. And of course that undergoes alpha decay, so we would drop down 2 and over 2, and we continue as long as there's alpha decay going that direction. That is how we would track it. The slides show that. In this case, radon-222 decays to polonium-218. When we're looking at beta negative, what we're going to be doing is converting a proton to a neutron, so we're going to be going down 1 and over to the right 1, which makes us move right diagonally. As far as an example from the chart itself, let me find the beta minus decay. Here we go. I'll get back to the, oops. Get back to the camera. Wrong one. Boom. There we go. The U-237 is shown here. U-237, radioactive, 6.752 day half-life. Beta minus shows 2 energies there, and that's because there's possibly be 2 betas, but this would be my Emax on the betas. We are dropping a proton, so we go down 1. We're getting a neutron, so we go over 1. And in this case, as I move it over, polonium-237, or PA. PA is palladium, not polonium, palladium. PA-237. Beta minus decay of the uranium-237. And it likewise, 8.7 minute half-life, will decay to thorium-237, and likewise it's beta minus, and so on and so on. And then we have a beta plus. Beta plus, keep in mind, is a conversion of a neutron to a proton, so we're going to go over to the left 1 and up 1. In this particular example, you're looking at 7-nitrogen-15 undergoes a beta positive decay to oxygen-18. And finding one on the chart of the nuclides here for us to take a look at. Got one. Get over to the ceiling camera, and as soon as I find it on here, yeah, ruthenium. Ruthenium 90 will beta plus decay. Keep in mind, neutron going away, so we'll go over 1. Proton coming into play, up 1. And Ru is actually, ruthenium. Rh is rhenium. And so we go to rhenium. And it likewise undergoes a beta positive decay. Electron capture, basically the same way. Now, electron capture on the chart of the nuclides is shown by a funny looking little E, and sometimes it will be by itself, sometimes it will also be represented and shown with a beta plus. And I'll just leave that to you. I found one here real quick. Let me get there. Ceiling. Yes, ruthenium 94, electron capture, beta plus decay. It would go over 1, up 1, lose a neutron, go to the proton, and here we have rhenium 94. And here you see an example of where we have actually 2 isotopes. Both of them are beta positive emitters, but they occur at a different percentage of the time for that particular isotope. Oh, I didn't have that on there. Let me get over there. Ruthenium, rhenium 94. You can see it's blocked out. Each side has a half-life of its own. Each side shows you that it undergoes a beta plus decay, and each side also shows you that it has multiple gammas associated with that decay. Now, I've got one last term I want to cover, and that has to do with activity. Now, we have discussed this, and you've studied it, and we just need to make sure that you're on board with it. We will look at the general term tonight, and then in part 2, we pick up and talk a little bit about the radioactive decay law. When we're looking at activity, it all started way back when we started studying all of this. We started discussing the fact that radioactivity deals with the atoms undergoing transmutation. They're changing. And the number of atoms that are doing that over a period of time, we decided and discovered that that really is a measure of what we call activity. It's a measure of the quantity of radioactivity transpiring, the number of atoms that are undergoing this transmutation per unit of time. And usually we express it in terms of minutes. But it can be expressed in any terms of time. It really doesn't matter. Originally, it was based on radium, because that was the work that was being done by the Curies. And as you can see, the traditional unit is Curie, named in honor of the Curies. But it was based on 1 gram of radium that would be in equilibrium, and it's the number of disintegrations that are occurring every second or so. It was D per S. The SI unit for activity is becquerel, or BQ. The equivalents you can see there, 3.7 times 10 to the 10th disintegrations per second, which is equivalent to 2.22 times 10 to the 12th disintegrations per minute. And all of that is equal to 3.7 times e to the 10th becquerel. And as you can see, the equation for becquerel is shown down at the bottom there. This is just, again, a reminder of the subdivisions that we can do, or the multiplications of kilo and mega can also be used to simplify communication. And then there's this term called specific activity. When we look at activity itself, it's not really a good measure of the size of what it is that we're dealing with. And to illustrate that, we need to talk about a little bit about specific activity and why it came about, and what it is. It's activity per unit mass, so it puts in curies per gram or becquerel per kilogram. Really, it's a concentration, how much of that isotope is in the sample or the piece that I'm talking about. The basis was originally done on radium, 1 gram of radium. The activity of 1 gram of radium is 1 curie. That's the standard that was developed. So the specific activity of radium is 1 curie per gram. But again, it does not speak to the mass. The mass that required to produce that level of disintegration, 3.7 e to the 10th disintegrations per second, will be a function of the number of atoms per gram of the material, or the gram atomic weight, or more commonly referred to as the mole. Give you an example of how this plays out and why it's important. If I look at a curie of pure cobalt-60, we would be looking at a mass of 0.9 milligram. Not very much at all. 1 curie in a very small amount. But now I take a look at the same measurement, 1 curie of uranium-238, and its mass would have to be more than 2 metric tons. Considerably different. Considerably different. And so we look at in terms of specific activity, which would really put us into more normalized terms, I guess is the way of looking at it. Now, as far as our discussion tonight, that pretty much concludes it. When we pick up in the second part, we're going to be looking at the radioactive decay law. This has been a little bit of a review. We've moved through the material rapidly. I encourage that if you are unfamiliar with anything that we've talked about tonight, that you spend a little bit of time, refresh yourself, go back to old notes, go back to the PowerPoint, redo this video clip, and re-familiarize yourself, especially with the chart of the nuclides, the different decays, how to maneuver through that chart of the nuclides, and also how to balance your radioactive decay equations. With that, we'll say good night, and God bless.